Hi, folks, and welcome to our next edition of Zog Science. Welcome to our second unit, where we're going to be taking a look at energy. We're going to be looking at energy in a lot of different aspects. We're going to look at how do organisms incorporate energy. We're going to talk about how do cells incorporate energy. And we're going to be beginning things by just talking about an introduction to energy and metabolism. So, an organism's metabolism transforms matter and energy. That's kind of our first concept we're talking about. And metabolism is the totality of an organism's chemical reactions. So all of the chemical reactions that are going on within an organism, when we put them all together, that is their metabolism. And it's an emergent property because, again, we're putting things together. And when you do that, it's going to give you new properties. A metabolic pathway is a specific pathway where we begin with a specific molecule and we end with a specific product. And metabolic pathways, we're going to take a look at several of those throughout the course of this unit. And when metabolic pathways happen, you don't typically just go from the beginning molecule and then you go directly to the product. Instead, it's a step-by-step process where we have our starting molecule and there's several reactions that will take place, and those steps are catalyzed by specific enzymes, and we'll talk more about enzymes and how they function later on. So energy is the capacity to cause change. That's kind of the general definition of what it is. And energy can exist in lots of different forms, and some of those forms can produce work. We'll talk about a couple of different types of energy as we move along through the unit. Thermodynamics is the study of energy transformation. So energy is not stagnant. It doesn't just stay the same kind of energy. It can very easily interchange between different types of energy, and that's what thermodynamics is studying that energy transformation. Now, in an open system, energy and matter can be transferred between the systems and its surroundings. So in an open system, basically like regular life, you can transfer that energy and also matter between the system, or in the case of biology, between the organism and its surroundings. In an isolated or closed system, exchange with the surroundings cannot occur, and obviously organisms or living things are going to be open systems, so we're going to need to follow those principles. Now, the first law of thermodynamics is that energy of the universe is constant. What that means is that the total amount of energy is always the same. And energy, therefore, cannot be cannot be created or destroyed, but it can be transferred or it can be transformed. So it can be changed into different types of energy, or it can be moved from one object to another. Another way to think about this first law is the principle of conservation of energy. Again, energy is not created or destroyed, it's just transferred or transformed. The second law of thermodynamics is that during each energy transfer or transformation, that process is not 100% efficient, and some of that energy is going to be lost as heat. Now, that doesn't mean that the energy is being destroyed, it just means that it's being converted into heat. And the problem with heat is that it is a very low quality of energy, and it can't really be used to do very much. It isn't really available to do work. And so what happens is that as that energy is being transferred into heat, what we call the entropy or the disorder or randomness of the universe is increasing. Because heat energy is a very low quality of energy, it's increasing the disorder or randomness of the universe. And so over time, the universe is going from having very ordered to disorder. Now, living cells are always going through these processes because they're constantly trying to transform or transfer energy. And spontaneous processes are ones that occur without energy input, and they can either happen quickly or slowly. Spontaneous in this sense just means that they are going to occur on their own. And when they do so, they're always going to be increasing the entropy of the universe. A non-spontaneous reaction is one that requires energy input and will not happen on its own. Cells are always trying to create ordered structures from less ordered materials. Your cells, organisms, your body, right? You are trying to build things. You're trying to put things together. You're trying to hold them together. You don't want them to become their constituent parts. You want them to stay ordered. Organisms are always, therefore, using energy in order to accomplish these processes, right? And so even though cells are constantly trying to order things, right, they are decreasing their energy locally. They're decreasing the entropy of the system. They are overall still increasing the universe's total entropy, because as they go through the process of using energy to build things, that process is inefficient. They're still creating heat. And so organisms are essentially, you can think of them as being islands of low entropy in an increasingly random universe. All right, so our second concept that we're going to talk about today is that free energy change of a reaction. The free energy change of a reaction tells us whether or not the reaction occurs spontaneously. So what we can do is we can actually do calculations to determine whether or not a reaction will occur spontaneously or not. And the way that we look at this is we first need to know how free energy works. So free energy is energy that can do work when temperature and pressure are uniform, such as in a living cell. So free energy is the energy that is available to do work. And the change in the free energy of a cell during a chemical reaction is the difference between the energy state of the final and the energy state of the initial products, right? So if we're talking about a chemical reaction, we're going to look at the initial and the final, and we're going to determine if a process has a negative delta G or a negative free energy, then that would be a spontaneous process, and it's going to occur on its own. We don't have to put energy in. If it is a positive delta G, then we're going to have to put energy into the process in order for it to occur. Remember that during a spontaneous change, the free energy is going to decrease and the stability of the system increases. So when we move from a higher G to a lower G, we are going to be occurring spontaneously, and that's because we're increasing the entropy of the system. It's also a more stable conformation, so it's got a more stability, and that's a big thing with molecules, with chemical reactions, is moving them into a more stable form. And also there's less capacity for work to occur when you are in that lower energy state. Now, there are a couple different kinds of reactions that can occur. There are exergonic and endergonic reactions. An exergonic reaction is one that proceeds where it is a net release of free energy and it is spontaneous, meaning that our delta G is negative. So we look at the free energy of the reactants. The free energy of the reactants is a lot higher than the free energy of the products. And so that means that the delta G is going to be negative. It is going to be decreasing. And the magnitude of the delta G represents the maximum amount of work that can be performed. An endergonic reaction is basically the opposite. We're going to be increasing the free energy of the products, and so therefore we've got to put energy in order for that to occur. That's going to be a non-spontaneous reaction because we've got to put that energy in. All right, that's all for our introduction. Thanks for watching, and I'll see you next time.